Well, hi and welcome everybody to this Royal Meteorological Society event. We are hosting this virtual event today on climate change impacts on the Arctic, Antarctic and high mountain glaciers. I'm Liz Bentley, I'm Chief Executive at the Royal Meteorological Society, and here just to do a welcome and some admin slides before I hand over to our chair, Bethan, in a couple of minutes. So first of all, I just wanted to run through Zoom. We'll be taking questions for each of the presentations. So there's a Q&A box at the bottom of the Zoom window. Please add your questions to the Q&A box and we will get through as many questions as we can during the panel discussion. You also have the function to kind of upvote a question. So if you see a question that you like and you want it supporting, underneath the question, there's a thumbs up sign. So if you click on the thumbs up, you'll see the number of people who are supporting that question, and it just helps the chair to prioritize which questions we will get to. So add questions and support questions that are in the Q&A. If you want to make the PowerPoint slide area a bit bigger, then I suggest you close down the chat and any other Zoom functions so you just see the slides themselves, and enlarge the screen so that you can see the full PowerPoint on the whole screen as well, so you can see the detail. And any technical issues, I would suggest just leaving the Zoom call, maybe trying a different browser. You can see the different browsers that we recommend for Zoom and revisiting. Hopefully that will sort things out. But yeah, any technical problems, please leave and then rejoin via the Zoom link. And then my final two slides are really just a little bit about the Royal Meteorological Society. So first of all, just to let people know that we have a Met Matters section on our website. You can see the URL link at the bottom of this slide. You can sign up to receive a newsletter. So every time we put new content on our Met Matters pages, you can find out more about new content that we're publishing. And it's a wealth of content on weather and climate. Also information about events such as this one as well. So I'd encourage you to go and have a look at the web pages and join the sign up to the newsletter if you wish to. And then finally, and I know many of you already are, but the Society is a membership organisation. So if you're not already a member of the Royal Meteorological Society, can I encourage you to take a closer look at some of the membership benefits, and there's a number of them listed here. But you can go to our website link again at the bottom of this slide and find out more about membership. Contact our membership team if you want to find out more, and hopefully join the Society. Great. Okay, so I'm going to hand over now to Bethan Davis. She's a professor of glaciology at Newcastle University, and her research quantifies how ice masses behave in different climates and different environments around the world. She's undertaken multiple remote polar expeditions to the Antarctic, the high Andes, and the Arctic. And she's won many awards, some of them you'll see listed in her biog. So she won the medal for the Antarctic Education and Communication by SCAR in 2022, and also the Lewis Penny Medal as well in 2014. So hand over to you, Bethan, for what looks like a really interesting meeting.
Thank you so much. Thank you so much. And thank you everyone to be here. I can see that our attendees are still going up. I can see we're now at 65 attendees. So that's brilliant. It's really nice to have such a large cohort of people. And we've got a really exciting lineup of speakers. So they've turned their cameras on so you can see them. So we've got experts in Arctic glaciology. We've got Professor James Lee from Liverpool University, who'll be talking about Greenland glaciers and Greenland ice sheets. We've got Antarctic specialists, Ella Gilbert and Mike Bentley, who'll be talking about the grounded ice, the land ice in Antarctica, and the floating ice around Antarctica, respectively. And then we've got experts in mountain climatology and mountain glaciology, Sihan Lee and Hamish Pritchard. And we also have experts in geopolitics. We've got James Jansen from the FCO in London, he's an expert in Arctic geopolitics. So I think we're going to have a very lively and interesting discussion. I'm going to invite our speakers to each give a very brief outline and an introduction into what they see as the kind of most important insights into their particular region of expertise. So we'll do that for about half an hour or so. Each of them will give a very short 5-minute introduction, and then we'll move into a panel discussion where we'll have hopefully a nice, deep, meaningful conversation about some of the real issues in land ice and glaciology and climate change today. From there, we'll move into an audience Q&A, so feel free to type questions into the Q&A, and if you like the question, upvote it, and I'll try and make sure that we get through as many of those questions as possible. So I'd like to start by asking Professor James Lee to talk about the Greenland Ice Sheet and climate change in the Arctic.
I'll take on mute. Thanks very much, Bethan. I'll just share my screen. Can everyone see that? Yep. Fantastic. So, good afternoon, everyone. Thanks all for joining. So this talk is going to be a very much a crash introduction to how weather and climate is being affected in the Greenland Ice Sheet. So for those of you who aren't necessarily familiar with Greenland, so the Greenland Ice Sheet is truly massive. It's one of the world's 3 ice sheets. It's about 8 times the size of the United Kingdom, or in other units, about 104 times the size of Wales. And its highest point is 3,200 meters above sea level. But in terms of the ice that's actually in Greenland, there's about 7.2 meters worth of sea level equivalent locked up. So we can strip all that ice away from Greenland. This is our best estimate of what the ice sheet looks like. But with the ice itself that is there, so just for reference as well, that isn't going to be what Greenland looks like anytime near in the future, thankfully. However, with the ice that is there, it's important to remember as well that the ice isn't static. It moves, it flows, and in some parts of Greenland, it can actually go up to 14 kilometers per year. So it's really sort of a dynamic landscape. It's not sitting still. So the way in which the Greenland ice sheet has been reacting to climate change over the past 25 years or so is that it's been losing a huge amount of ice. So the way in which it loses ice is through a combination of iceberg calving, so discharging icebergs into the ocean, and the main focus of the talk today, which is going to be on surface melting. So just to give an idea of where the ice sheet is melting and how that's been changing on this slide over the past 30 years or so, is you can see that from between the early 90s and the early 2000s, there's not really been that much change going on. But as we move into the 2000s, we start to see more of these reds. This is the amount of surface lowering of the ice sheet, and you see real hotspots around the edges, especially in the western sector and the northeastern sector as well. So why is this? So as we get increased climate warming, then we have changes happening to the ice sheets, which means that it's not very good for this mass. So hopefully, in an ideal world, an ice sheet should have equal amounts of accumulation above the 0-degree isotherm, and that should equal the amount of ablation or mass loss that happens below the 0-degree isotherm. However, if, for example, we were going to lower this isotherm, so if we were going to decrease the annual temperature, then this would mean that we would decrease the area that's melting, we'd decrease the ablation area. But if we were going to increase the temperature by the same amount, the shape of the ice sheet means that we're actually going to start melting a proportionately larger area than we would otherwise. So that is really important for future climate change. So for every degree, every decimal of a degree change, we start to melt more and more of the ice sheet. So that's the long-term climate perspective. But we're also seeing in the last 10, 15 years or so, an increase in extreme surface melt events and also rainfall events, so rain on snow, rain on ice events, and these have quite significant impacts on the ice sheets as well. So just to give an idea of what these things actually look like, so this is the aftermath of a rain event that happened in 2021, and it was 1,800 meters above sea level. So this should be completely white, it could all be snow. However, we can see that there's huge amounts of meltwater. We've got streams and rivers as well. And that's just not a flash in the pan. That doesn't mean that you have the melt event or the rainfall event and that's it. This actually has a long-term impact on how much the Greenland ice sheet will melt. And the reason for that is as the meltwater percolates through the ice, you start to get these ice lenses. And these ice lenses can actually increase the likelihood that we'll get surface runoff. So it makes it easier for that meltwater to get. One of the other reasons as well that weather is actually impacting the ice sheet is actually due to the colour, the reflectiveness of the ice sheet surface. So from the title slide, might have seen sort of on the left-hand side, this is sort of early melt season. We've got lots of snow on the ice sheet, very bright. Or in the mid to late melt season, you see this really dirty ice coming through, and that's a combination of glacier algae, so-called cryoconites, and also particulate matter that's from within the snow and also transported. Why is this becoming increasingly important? Well, in the past few years, we've had increasing amounts of wildfire events, especially in North America. Might remember that there was one last year, so this is a map of all the smoke that was coming off the wildfire events last year. And this has actually been transported in quite large amounts over to Greenland. So this is a video from a friend that was taken in the middle of the day in the southwest of Greenland, and you can see that the sky is really, really dark, and that smoke, that particulate matter, is being transported towards the ice, which is then making it more. But then, with this meltwater, where does it actually go? It doesn't all run off across the surface. It actually then also can be transported into the ice sheet, down to the base, and be evacuated out of the front of the ice sheet quite efficiently. So on the right-hand side here, we've got an enhanced satellite image, which is showing in white the sediment plumes coming off the margin of the ice sheet. And these also have impacts on not only the biological productivity of the oceans and the fjords, but also because it's delivering cold, fresh water into the North Atlantic. That also can impact the oceanography and therefore North Atlantic. So to summarize, it might sound like a bit of a dark future for Greenland, but it's not necessarily. We can actually sort of help Greenland recover by limiting and reducing further climate change. There's been lots of conversations recently in the media about geoengineering. This is not really an option for a continental-sized ice sheet. So I've listed some reasons there in what I think the order of importance are. And I'd say the only proven thing that will work is to reduce global carbon emissions. And with that, I'll stop.
Thanks, James. There was an awful lot to think there, and I really like the way you were bringing together, fires and ice and oceanography, and it just shows what a connected system this is and how everything impacts everything else. Thank you very much. We'll come back to you in a few moments. We're going to move swiftly to Antarctica. So I'm going to ask Dr. Gilbert from the British Antarctic Survey. Ella Gilbert is a research scientist at the British Antarctic Survey. And I'm going to ask her to tell us about the floating ice around Antarctica.
It would help if I shared my slides, wouldn't it? Lovely. Okay, yeah, so flipping to the Southern Hemisphere now and thinking about the ways that climate change is reshaping or shaping Antarctica. A very brief kind of summary of where we're at for the Antarctic. There's this kind of east-west divide primarily, which you can see on this map over on the right. And essentially what we're seeing is quite strong warming over the Antarctic Peninsula and the West Antarctic ice sheets. And then on the other side, we've got the East Antarctic, which has been, slightly stable, much more stable comparatively. And the net effect is that there's a very slight warming trend over the last several decades in Antarctica. But temperature is only one part of the picture, and we've seen lots of shifts in weather patterns and also a warming ocean around Antarctica, especially in this kind of western sector. Especially in the wind kind of changes have seen a shift of the very strong circumpolar westerly winds that kind of characterize Antarctic climate towards the pole, and that's having a variety of different impacts on the atmosphere and oceans. Just like in Greenland, we see lots of extremes in Antarctica, and the number of extremes and their consequences are starting to increase. There's a nice summary paper led by Martin Seeger with some familiar authors up there as well. We're seeing extremes in a variety of different sectors of Antarctica's climate. So whether that's temperature, heat waves, extreme precipitation events, including in some cases, like in Greenland, rainfall events. That's what this picture is showing, these sad baby penguins who get wet in rainfall, and they're not so well protected against hypothermia because they're babies, and this can cause huge problems with the collapse of entire breeding populations of penguins. We've also seen lots of extreme conditions with respect to sea ice in the Antarctic in the last few years, and even the collapse of entire ice shelves, including like this example down here, the Larsen B ice shelf. One specific example is this one from 2022, which hit the east of Antarctica in March. And it was basically associated with an atmospheric river, which these long kind of filament shape features in the atmosphere that deliver huge amounts of heat and moisture. And you can see in this animation with the kind of red colors, the amount of heat that was delivered. And this caused a heat wave that drove temperatures from their normal, very, very sub-zero conditions to around 40 degrees Celsius above average, which is equivalent to, I don't know, in the UK, seeing a 55-degree day on a day like today. So it was a really, really enormous change in temperature that had very significant consequences for the ice sheet and also for the sea ice around the continent. These sorts of extreme events can trigger very significant changes. So whilst we have the kind of background of climate change, which preconditions and provides the context for change, it's often extreme events that trigger the actual change themselves. So basically is the straw that breaks the camel's back. This diagram kind of summarizes some of the impacts of atmospheric rivers and shows how they can combine with other extremes, such as foehn winds, which are generated when air flows over steep terrain. These are very important. It can result in changes to ice shelves, to sea ice, to the ocean environment around the Antarctic, and in some cases, as I mentioned on the previous slide, can cause the collapse of ice shelves. And this is what is thought to have been the cause of the Larsen B's demise. This is also something that's continuing to happen. This is an example from very recently in that 2022 period. This is the Conger Ice Shelf in East Antarctica, a region that was previously thought to be very stable. So it was quite a surprise when this one collapsed as a result of the storminess and also a few sea ice things, again, showing the kind of interconnectedness of the polar environment. And it would be remiss of me not to mention the pretty mind-blowing extremes that we saw in sea ice last year. You may have seen some of these headlines in the news, but Antarctic sea ice was pretty much off the chain last year and the year before. This plot shows a kind of annual cycle in Antarctic sea ice. All the green years are every year apart from 2023. The black is the average and pink is 2023. And you can see that there was a record low minimum, which is also in this map here. A very slow freeze up meant that by July, there was this huge area of sea ice missing that was equivalent to the size of approximately the world's 10th largest country. Overall, it meant that there was a really low maximum winter extent, which again is shown in this satellite image. And then it kind of recovered to near normal, and that has sort of continued, a heavy emphasis on the sort of until about now. So in summary, we're seeing considerable climate change in the Antarctic, both the atmosphere and the ocean. That's having impacts on weather patterns. It's the background of climate change is preconditioning changes, and extreme events often act as a kind of trigger for significant changes like ice shelf collapse or sea ice loss. And there may be some evidence emerging of a kind of regime shift in sea ice. Thanks.
Thanks, Ella. There was an awful lot to think about there, and this idea of extreme event that triggers change that may then act to be self-perpetuating or to accelerate is very interesting, and I'll think about that further. I'm going to ask Mike Bentley to take us through some of the changes we're seeing in the glaciers and the land ice around Antarctica. Mike's a professor of polar geoscience at Durham University, and he wants to tell us how the Antarctic Ice Sheet works.
Thanks, Bethan. So I'm just going to spend about 5 slides just trying to answer 4 or 5 questions that I get asked quite a lot. One is, how does the ice sheet work and why are we worried about it? Secondly, what's happening spatially across the continent? How's that been changing through time? And then the final question I'll answer is, where are we heading? What does the future hold? So this is just a little block diagram of the Antarctic ice sheet. Ice sheets are pretty simple at their heart. They accumulate snow, they flow under their own weight to the margins, where in the case of Antarctica, they start to float and you form an ice shelf. Now, unlike Greenland, where James showed a lot of the loss of mass at the edges is by melting, actually that's quite a small component in Antarctica on the surface melt. It is expanding in Antarctica, but still a relatively minor amount. And most of the mass is lost by carving of icebergs off the front of the ice shelves, or by melt underneath the ice shelves, beneath these ice shelves. And it's this particular effects on the ice shelves that's why we're worried, because the ice sheet is held back or buttressed by some of these ice shelves where they run aground or they are in big embayments where there's friction at the sides. It sort of holds the ice back. So if we lose these ice shelves by thinning, melting, and cracking them, carving them off, then the ice sheet will start to flow faster. It will retreat back into deeper water, so it will then retreat even faster, and we get this runaway effect. So we're worried because of this buttressing effect of ice shelves and the runaway effects if we lose those ice shelves. In terms of where that affects us, this is what Antarctica would look like if you peeled back all the ice. And Ella showed you, we tend to talk about Antarctica in 3 main areas: West Antarctica over here. East Antarctica is the much larger component of Antarctica, and the Antarctic Peninsula is the much smaller part. East Antarctica is mostly above sea level, all these brown colors. If you peel back the ice, it sits mostly above sea level like a normal continent, but with a couple of areas called the Wilkes Basin and the Aurora Basin that sit below sea level. And then West Antarctica sits mostly below sea level. And this is where we're most worried, because this is the areas of the ice sheet that are really susceptible to those loss of ice shelves and retreat back into deeper and deeper water. And we get this runaway, we call it an instability, and runaway loss of ice and sea level rise. So it's the ice that's grounded below sea level that we worry about in West Antarctica and in these marine basins in East Antarctica. So what's happening to the Antarctic ice sheet at the moment? Spatially, this is a map which is showing the change in the elevation of the ice sheet over the last 10 to 15 years or so. Per year, in meters per year. So where you see the warmest colors, these browns through to this rather dark red, that's loss of ice, going to about 10 meters of ice per year. So a site over here is losing 10 meters of ice per year consistently for some decades. Where you see the slightly bright color, you getting very, very slow accumulation or thickening of the ice, but at much lower rates, less than half a meter per year over parts of East Antarctica. So you see straight away that those bits of marine ice I was telling you about, marine grounded ice, are where we're worried. We've got a lot of thinning in these areas. We've lost some ice shelves. See a lot of thinning in the peninsula. And then some of those marine basins I was telling you about in the Aurora Basin and possibly in the Wilkes Basin, we're starting to see some early warning signs of ice mass loss. So that's the pattern. And I'll come back to that in a moment when I talk about sea level. But the the pattern through time is shown by this diagram here. And we've broken it down into East Antarctica, West Antarctica, and the whole of Antarctica, with the Antarctic Peninsula in the brown there. So I'll just go through each of them. East Antarctica is this yellow band. And what we're seeing here is through time, from the mid-90s through to the mid-2010s, we're looking at the amount of ice that was being lost, either in gigatons, that's billions of tons, or in the sea level contribution in meters. And this is cumulative. The units here are difficult, gigatons. Even scientists don't really know what a gigaton really feels like. A 1 gigaton is the same as twice the weight of all the people on Earth. Or another way of thinking about it, depending on your units, is 200 million elephants. So 1 gigaton, 200 million elephants. And you can see that the Antarctic Peninsula was losing about 500 times that, or has lost about 500 times that since the mid-90s. And that's the smaller component of loss. West Antarctica is losing much more, this green band. So that's lost over 2,500 gigatons since the mid-90s. East Antarctica has just got this tiny gain. It's sort of really close to zero, but it's a tiny gain in mass because of this tiny amount of thickening here, which is due to increased snowfall. It's a long-standing prediction of global warming that with a warmer atmosphere, more moisture will get more snowfall. And in East Antarctica, that's not yet offset by these losses in the red areas, although we think it will be soon. And then the total is this pink color here. And you can see that overall, Antarctica has lost over 3 trillion tons or 3,000 gigatons of ice since the mid-90s. So where are we heading? So this is the latest sea level projections from the Intergovernmental Panel on Climate Change. Now, this is Antarctica and Greenland that James was talking about, and mountain glaciers and thermal expansion. And you can see that we have choices. So by 2100, if we stick to a low emission scenario, the blue bands, we could have sea level of just over 0.5 meter. If we stick to business as usual, high emission scenarios, we could get sea level rise of just over 1 meter by 2100. And actually, due to some ice sheet physics that we're still debating in the glaciological community, we can't rule out actually much higher values. We think it's fairly low likelihood, but it's possible that we could get over 1.5 meters. And of course, sea level doesn't stop in 2100. If you go to 2300, the low emission scenarios are keeping us kind of between 0.5 meter and maybe 3 meters. High emissions from 2 meters upwards, and we can't rule out 15 meters on this low likelihood, high impact storyline. So that's where the sea level story is taking us, but we do have these choices. And I think it's really important to point out, although we will have sea level rise, we can choose as a society how much sea level rise we have. So I'll leave it there and pass back to Bethan.
Thank you, Mike. It was really interesting, and I think it's useful to think about impacts as beyond 2100. Many of our younger audience might well be still here in the year 2100, and some of them may go on to have children and great-grandchildren and future generations, and not that dissimilar, not that separate from us, who could live to see 2300. So it's really not that long a timescale, although it's a very human timescale to be thinking about. I'm going to move now from the huge ice sheets of the world to the world's highest mountains. I want to ask Sihan Lee to talk to us about the world's glaciers and the climate in the mountains. Sihan is a lecturer in climate science in the Department of Geography at the University of Sheffield. Thank you, Sihan.
Thank you, Bethan. I'll share my screen. Hopefully it works. Can you see my screen?
Yeah, that's great.
Great. So my camera is on my laptop. I'm playing the slides from my desktop, so my eyes might wander off, so apologize for that. So thank you for that introduction, Bethan. And today I'm going to briefly talk about climate change impacts on high mountain glaciers. This is a very big topic. Most of what I'm going to talk about today are thoughts and reflections from working on these 2 NERC-funded projects. One of them is Deplete and Retreat, which is focusing on the Andes, thinking about the sensitivity of water resource availability in glacier rise catchments to the changing supply of snow and ice in a changing climate. And the other project is Sajak Nepal, which is thinking about mountain multi-hazard over the Himalaya Nepal region. So I'm going to put a slight focus on the Himalayan Andes throughout this talk. So mountains are the world water towers. They capture water from the atmosphere and store them in snow and glacier ice, but as well as also in permafrost, wetlands, lakes, and rivers. The supply of water from mountains is very crucial for a lot of communities, both along and downstream the mountain ranges, supporting essential needs such as domestic consumption, irrigation, hydropower generation, and ecosystem service. So this is showing the Andes, but similarly in high mountain Asia region, which includes the highest mountains of the world, these extremely high altitude glaciers provide seasonal water to at least 2 billion people. And quite often we think about glaciers, but also the whole system actually matters a lot. As part of the cryosphere system, we have snowpack, we have wetlands, lakes, and rivers. So they all form part of the cryospheric system that we're concerned about. So climate change is having very rapid and dramatic impact on the mountain cryosphere, the land cryosphere. So this is a very simple schematic that I take from a paper that came out a few years ago. Although it's very simple, but I found it very intuitive to think about the hazard associated with drastic rapid changes in the mountain cryosphere. So these cryospheric changes are spatially and temporally complex. We were seeing snowfall amounts increasingly delivered by fewer but more intense extreme events. And we see snow avalanches, glacier collapse, but also glacial climatic feedback moderating glacier mass loss and potential increase in landslides, mudslides, debris flows, as well as glacial Lake outburst flood, which have drastic impact on infrastructure, road, houses, agricultural land downstream, as well as release of greenhouse gas due to the thawing of permafrost in these mountain glacial areas. So very drastic changes that we're already seeing in the climate system. Now, if we look at some of these most impactful weather and climatic related disasters. So this is a figure showing a summary for 2021. We're seeing the different types of the most impactful events, and these are shown by the different symbols on the left-hand side here. We see convective storms, tropical cyclones, flood, glacial lake outbursts, drought, heat waves, and fires. And these different colors represent the extent to which we know the role played by human-induced climate change. So this is a summary for 2021. If we look at the picture for 2022 again, we see similar kind of very wide across spatial distribution of this really dramatic impact of weather and climate-related events. But what I found very interesting related to what we're discussing today is that this kind of hazard that originated from mountain glacier, from mountain cryospheric changes made the list in both 2021, 2022. If I could point your attention to, this is 2022, this bit here is showing a glacial lake outburst that happened in Europe. And if I flip back to 2021 here, we also see a glacial lake outburst over the Asia region. So we are seeing very visible, very impactful results from these mountain glacial changes in different parts of the world. So now if we look at how much things have been changing, this is a figure taken from the high mountain area chapter in the IPCC special report on ocean and cryosphere in a changing climate. This is showing a synthesis of trends in mean annual surface air temperature in mountain regions based on roughly 6,400 observation stations, and they are aggregated into 38 data sets that separately reported by 19 different studies. and each line refers to a warming rate from one data set. And they are calculated over the time period indicated by the horizontal extent of each of the lines. And the colors indicate the different mountain ranges that were being studied. And the thickness of the line represent the number of observational station actually went into the data set and went into the study. If we look at, for example, high mountain Asia, which is shown by this pink salmonish color here, what I want to draw your attention to, sorry, I should point out that the y-axis is showing the warming rate per decade. Two things I want to highlight with this figure is that we are seeing almost universal warming across these different mountain regions in the world. But if I can point your attention to these different salmon pinkish lines that represent high mountain Asia, the different regions are presenting different rate of changes. So a lot of spatial heterogeneity that we are seeing in terms of rate of change and spatial patterns. And the other thing that I want to point your attention to with this figure is that the number of available stations is very limited that went into some of these studies. As you can see, very, very rarely that we see on the order of 100 stations went into the study, and sometimes it's on the order of 10, even a single station that goes into these studies, these results that we're seeing. Now, if we look at future projections, this is a study that came out shortly after the special report. This is focused on high mountain Asia region, which include the Tibetan Plateau. What the authors did is that they evaluated a range of different models and selected the 10 best performing models to take forward to make future projections. And we can see that in the wider high mountain Asia region, even in the most optimistic ISSP scenarios, we're seeing warming into the future by 2100 and drastically decreasing snow cover extent and slightly increasing in total precipitation in this very optimistic low emission scenario. But something else I want to draw your attention to is if we look at this this time period, this is comparing the historical simulation compared with observation record. We can see for temperature, there is a relatively good agreement, but for snow cover extent and for precipitation, there is very drastic difference between what the model is saying and what the observation is showing. And this goes back to what I mentioned earlier, is the desperate need of more observational record to calibrate the model and to give us confidence in what the model is saying for these high mountain areas. So I'm showing the future projected change for high mountain Asia. And as part of the Andes project that we're doing, we're going to generate high resolution future projections over different part of the Andes at as high as 4-kilometer resolutions. So stay tuned for that. Now, if we look at glacier projections and looking at the different glaciers, how they are projected to change, this is taken from the State of the Cryosphere report for 2023. What I'm showing here is the glacier volume change until 2300, so reflecting back on what Bethan had mentioned, looking even further ahead beyond 2100. And this is in comparison to, relative comparison to 2020. So using 2020 as a reference period, that's why before 2020, you see this percentage that's higher than 100%. It is because prior to 2020, we have higher or more ice coverage over these regions. So the different color lines represent the global temperature change at the end of the century, 30 years versus pre-industrial level of the different models that were used to produce these future projections. And the black line denotes the evolution of prior to 2020. And the thick horizontal line here and here represent the best estimate of the remaining glacier volume for each of the global temperature levels by 2100. So whether we warm up the planet by 1.5, by 2 degrees, by 3 degrees Celsius. And so this is the picture. What does the picture look like for glacier volume change for the high mountain Asia region? And if we look at a bit further south of the equator, looking at the Patagonia and southern Andes, we're seeing also very drastic decrease in terms of glacier volume changes by 2100 and 2300, even under this very optimistic goal of keeping global temperature rise at 1.5 degrees Celsius. And if we then again look at tropical glaciers, which include Africa, South America, and Indonesia, the picture is even more grim. Because if we think about these different regions of mountain glacier for high mountain Asia, which includes some of these really high, extremely high altitude glaciers, which provide seasonal water to at least 2 billion people, these will lose most of their ice by if we warm up the planet by 3 degrees Celsius, whereas if we keep the warming level at 1.5, we preserve more of the ice coverage. Whereas for glaciers of Patagonia and the southern Andes, these have some of the fastest receding glaciers in the world, but models are showing that loss will slow down and will preserve about 50% of the current ice volume by 2300, but we'll lose more if we keep warming the planet to 3 degrees Celsius. Whereas for the tropical glaciers, the reality is that as of 2023, these tiny glaciers near the equator in Africa, in South America, in Indonesia, have already lost most of their ice, and those glaciers that remain are already quite small and at very high altitude, which help them from protect them from the warming. And according to these projections, at least some of these very small patches of remaining ice likely will be preserved at 1.5 degree warming. And these are super important because they are of really high symbolic importance to the local communities. And with that, I guess the main take-home message is that similar to what Mike and Bethan just said, there is quite a difference, even with tens of degree warming into the future, and there's a lot that we can do and we need to do in order to prevent these glaciers losing volume dramatically by 2100, by 2200, by 2300. And with that, I will stop sharing.
Thank you, Sihan, and it's true, we have everything to play for, and every 1/10 of a degree matters. Just a reminder to please, there's at the bottom of your screen, you'll see a Q&A and a chat. The chat is disabled for viewers, so please put your questions in the Q&A rather than the chat. And you can also upvote questions if you want a particular question to be answered. So we're going to stay with high mountains, and I'm going to ask Hamish to talk about the glaciers of the high mountains. So something more glaciological focus.
Thanks, Bethan.
Hamish is a research scientist at the British Antarctic Survey and a glaciologist at the British Antarctic Survey.
Thanks, Bethan. Yeah, just following on from what Sian was talking about in terms of the changes occurring in high mountain glaciers, I'm just going to give a quick example of what that means for people living downstream. So there's the distribution of the mountain glaciers. Ignore Greenland and the Arctic for the moment. And the interesting point, I suppose, in blue, you can see there, the interesting point, I suppose, is that these lower latitude glaciers are in quite close proximity to large populations downstream. And so the subtitle for this little bit is, why do glaciers matter to us? Mountains are great generators of precipitation. So, and that's because of things like orographic uplift, which this audience I'm sure will be well aware of. And in fact, about half of the world's fresh water is generated by mountain precipitation. And being cold at the top, they're also good at storing that precipitation. So as Sian mentioned, in winter you get a winter snowpack, and then spring that starts to melt off. And in summer, a seasonal snowpack is all gone. And the difference that the glacier makes is that it'll get the winter snowpack forming there. In spring, that snowpack will melt off and deliver water downstream. But because there's glacier ice there, that melting will continue all the way through the summer. It's not a seasonal phenomenon, it's a perennial phenomenon as long as the glacier is there. And so glaciers have this unique role hydrologically of being able to sustain this water supply throughout the summer. So then the question is, well, how important is this service? I'm going to just zoom in on the high mountain Asia. This is perhaps the mother of all examples for what role this service might play, because there's such a large extent of mountain glaciers, about 90,000 glaciers there, and a couple of billion people living at least broadly within those catchments downstream. So here we are. Here's a map of that area. The black shows the glaciers going through the Himalayan arc up into the Karakoram. The green colors and the blue colors are the population distribution. So you can see the Ganges plain, Indo-Gangetic plain down just immediately south of the Himalayas there. And then the major rivers flowing down. So there's the Ganges tributaries going down into India, the Indus tributaries going down into Pakistan. The Brahmaputra is in southern Tibet and curves around to Bangladesh. And then to the north and the west are the rivers going off into Central Asia. And these are already well-used water resources. So here's a map of where the hydropower dams and irrigation barrages are. So these are the points at which that meltwater and precipitation is extracted and used. But it's also an area of huge expansion. So all those blue circles there show where there are more hydropower dams either under construction or planned. So there's a huge expansion in that use of water. And what the next map I'm going to show is I'm going to take out each of those catchments for those dams and just show where what the water inputs are for each one, and we can look at how important the glacier contributions are. So there's what I described. Just there are all those catchments shown as pie charts. Each pie chart shows the amount in pale blue, the precipitation that's going in as an input into that catchment in a climatologically average year. And then the very dark blue is the meltwater coming off from the glaciers that's in balance. And then the mid blue is the extra meltwater that's coming off because the glaciers are shrinking. And so overall, what we can see there throughout those catchments is that the dominant source of water for those at each of these places, even though they're quite high up in amongst the mountains, is precipitation. In total, the volume of water that's coming from the glaciers is actually substantial. It's about enough for 220 million people to survive on each summer. But the rainfall dominates everywhere. And of course, in this region, it's the precipitation is primarily arrives in the summer monsoon when the melt is also occurring. And so they compete against each other. And so the melt is arguably less important than this annual picture when the summer monsoon is in play. But of course, the question then is what happens when those rains fail? We can look at that by looking at the driest year on the record. So this is the same picture, but in the time of drought. This is the driest year within a 60-odd year record of measurements. And this is in the peak month for glacier contributions in each summer. And so the picture has markedly changed. The precipitation has reduced and the melt has more or less stayed the same in quantity. So the relative importance of that melt is much higher. So if I just now, actually what I could point out is that in particular, the importance of melt is particularly strong in the west, where the summers are relatively drier and the winter snowfall contribution is more important. But you can also see in Nepal there, almost all of the runoff input to those catchments in the middle of a drought is coming from glaciers. If we collapse those back down to their true geographic locations, we can see that they cluster in particular around the Indus tributaries and some of those Central Asian rivers up to the northwest. And those are areas where there are very dense populations. They're major centers for irrigation and hydropower. So the Indus catchment, the Indus Basin has the world's largest system of irrigated agriculture. And in pink, what was highlighted in this map are areas that have been identified as particular risk of conflict during natural stresses like droughts. And so what we could summarize is to say, I asked at the start, why do glaciers matter? Well, the particular niche role that glaciers play is to protect society against peak water stress. So they're not all that important during an average year, but in droughts, they become very important because the precipitation inputs drop away. But we can see, I mentioned that I was showing the balance and the imbalance melt, the contribution, which the sustainable and the unsustainable contribution in those two shades of blue. The combined total is about 1.6 times the sustainable rate. So this is not a sustainable water supply. And a lot of these developments for hydropower and irrigation and urban expansion and so on are occurring during a period of water glut as these glaciers shrink, and that will not last. So it's this service protecting society against peak water stress, which will be lost as these glaciers disappear. Thank you.
Thank you so much, Hamish. That was fascinating. It's interesting to juxtapose that to the previous talk where there was more discussion perhaps of glaciers as a hazard and then thinking of them now as a resource. So thank you very much. All of the change in the ice that our panelists have been discussing likely has geopolitical consequences. So I'd like to ask James Jansen to tell us about this. James is an expert he's the UK Senior Arctic Lead and Deputy Head of the Polar Regions Department in the FCDO, and he leads the UK engagement in the Arctic. So James, if you'd like to share your slides, that's great. I can see your slides and take it away. Right, James, you're muted at the moment. I still can't hear you. I still can't hear you. I think you're connected now. Can you say something now? No, I still can't hear you. Okay. James, I'm going to leave you to solve that and we'll come back to you. So if you work on that in the background, I'm going to ask Hamish to come back because we've had an interesting question in the chat, which you might like to answer, which is how do we measure this retreat, this shrinkage of glaciers? How do we know that glaciers used to be bigger and how do we know how quickly they're shrinking?
Yeah, so there's two sides to that. It's relatively easy these days. It wasn't until quite recently, but mostly it's done by satellites, so by satellite imagery and satellite altimetry. And so for some of the glaciers, it's relatively easy to see where the end of the glacier is, the front of the glacier, and you can see that visually in satellite images. Some of them, particularly in high mountain Asia, they're covered in rock debris, and it's quite difficult to work out where the front is. But so the other approach is to measure how their volume is changing, how their surface height is lowering through melting. And there's a couple of ways of doing that. One would be through photogrammetry, which is the sort of traditional way of mapping the landscape with airborne photography with stereo pairs. And another way is to use satellite altimetry, which can be laser or radar in particular. And that'll bounce a signal off the surface and measure what the height change is. So they're pretty well established methods for measuring changes in the extent and the volume of these glaciers.
Brilliant. Thank you so much. James, do you want to have another go at speaking?
Can you hear me?
Yeah, I can hear you.
Okay, I'm not sure what happened there. It was working earlier. But anyway, good to be back with you. Let me just share the screen. Okay, and hopefully you can see that okay.
Yep, that's all good.
Perfect. All right. So, as you said, Bethan, I'm going to focus on the Arctic, but I thought I'd just start actually with a little bit of a comparison between the two polar regions. So, no better way to do that than with some maps. On the left-hand side, we have a map of the Antarctic, and obviously we've got the Antarctic continent there, surrounded by ocean. Now, the Antarctic is managed through an international treaty, the Antarctic Treaty, which has its origins back in the 1950s. And the UK is a party to that, and the parties to the treaty gather every year to agree and decide management measures and protocols for Antarctica. But broadly, the Antarctic Treaty sets the context. It preserves the continent for peaceful cooperation and for science. Now, if you look at the right-hand side on the Arctic, you've got an ocean surrounded by landmass, and of course that is all national jurisdiction. And so the context there and the way the UK engages in the Arctic is very different. So just focusing a little bit more then on the Arctic, by which I'm referring broadly to that area north of the Arctic Circle. So you've got here a nice map showing the 8 Arctic states. So those states that have territory north of the Arctic Circle. So the US, Canada, Denmark for Greenland, Iceland, Norway, Sweden, Finland, and of course Russia. Noting that Russia there is about 40 to 50% of the Arctic, so it plays a fairly substantial role in relation to Arctic affairs. Now, the Arctic, of course, during the Cold War was, a zone of confrontation, effectively. But as the Cold War thawed, there were some suggestions for what stronger cooperation in the Arctic could look like. So Mikhail Gorbachev, in his 1987 Murmansk speech, proposed that the Arctic states could come together around a shared commitment to protect the Arctic environment. And so the Arctic Environmental Protection Strategy was effectively born, and environment ministers met for the first time in 1991. Now, over the successive few years, that idea grew a little bit further, and the Arctic Council was then established in 1996 through the Ottawa Declaration. And the Arctic Council and the Ottawa Declaration effectively set out a framework for the 8 Arctic states, together with the indigenous people of the Arctic, to manage the Arctic for the purposes of its future sustainable development. And just note where the UK is on that map, because I'll come back to that in a minute. So the Arctic Council then has been operating effectively since 1996, had its first ministerial in 1998, and that's when the UK joined as an observer state to the Arctic Council. The kind of the workhorse of the council, if you like, are the 6 working groups. I've just given an indication of those on the right-hand side there. So, for example, you've got the Arctic Contaminants Action Programme, you have the Arctic Monitoring and Assessment Programme, and so on. So there's a really considerable body of work taking place under the auspices of the Arctic Council, focused on the environmental management and sustainable development of the Arctic. And the Arctic states, together with observer states like the UK and others, are very heavily engaged in that and contribute very much to that. That has been operating pretty much on a consistent basis since, as I say, 1996. And I suppose there has been this period of Arctic exceptionalism in a way over the past 25 years, where cooperation in the Arctic and indeed the polar regions more broadly has risen above and beyond wider global events, including the annexation of Crimea in 2014. Now, the Russian invasion of Ukraine was a step too far, and the other 7 Arctic states at that point decided that they would pause all cooperation with Russia in the Arctic Council. Now, the chairship of the council rotates every couple of years. Norway assumed the chair in May last year, and they have been working hard since then to resume technical cooperations at a very sort of scientific and technical level in the Arctic Council, and that is now kicking off again, including with Russia. As I said at the start, they're 40 to 50% of the Arctic, so that kind of collaboration there at a very technical level, that data exchange, is really important to the future management of the Arctic itself. But nonetheless, the lack of that political engagement itself has consequences, which I'll come on to in a minute. In terms of the UK's interests then, I asked you to note where we were on the map earlier. The UK geographically is the nearest non-Arctic state to the Arctic. So what happens in the Arctic has a very genuine and real impact on us here in the UK. And so we've been engaging in the Arctic one way or another for many, many years through the Arctic Environmental Protection Strategy and, of course, through the Arctic Council as well. Our long-term vision for the Arctic is for it to continue to be a peaceful and stable region characterized by cooperation. And the government set out its Arctic policy framework, which sets out more of what that looks like in practice. But a lot of that is based around partnership and collaboration, both with the Arctic Council, but also with the Arctic states themselves and the indigenous people of the Arctic as well. But a lot of our engagement is underpinned by science, you know, we have a huge and a very significant and very worthy body of science, and that really helps to consolidate our engagement on a much wider range of issues there. But the sands, as ever, or indeed the snows, are shifting in the Arctic as elsewhere, and I've touched on some of the challenges already. And we've just heard from some fantastic speakers about the environmental changes, the climatic changes that are taking place in the polar regions. And in the Arctic, of course, with the significant melting of the ice sheet, but also of the sea ice, also with the wildfires taking place, there are a number of challenges that we need to be thinking about managing. And one of those is that the Arctic inevitably is opening up much more broadly to a wider range of people. So there is greater accessibility in the Arctic as the ice starts to melt, whether that's for security purposes or for shipping purposes or for tourism, for example. There is, alongside that, of course, a real push and enthusiasm for Arctic resources from some quarters. Critical minerals is one of those things. The Arctic is very rich in critical minerals. Greenland, for example, is very rich in critical minerals, but has a very nascent mining sector. So there is a lot of interest in thinking about the opportunities that the Arctic might have to offer in that respect. And there will be new supply chains emerging depending on where critical minerals are exploited and who exploits them in order to support the green transition, which we are starting to pursue. There will also be the potential for increased tension. So if we have additional actors in the Arctic, whether they are state actors or whether they are commercial enterprises, there will be an increase in the number of actors in the Arctic, and that has the potential to raise tensions and potential for conflict there as well, particularly in the event of natural or man-made disasters. And while Russia remains engaged in Ukraine, the voice of the Arctic Council, because it's not meeting at that political level, is arguably diminished. And so Russia's actions are adversely affecting the role and the importance of the Arctic in what is a really critical time for the region and for the environmental change that's taking place there. And related to that, we are seeing, of course, the potential for new strategic alliances to emerge. So Russia has been very proactive in thinking about new alliances that it can help build to shore up its position in the Arctic, and as an Arctic state, thinking about engaging with some of the BRIC countries, for example, but also thinking about how it can make the most of access to the Arctic and Arctic waters as the sea ice retreats and opens up the Northern Sea route, for example. And it's recently introduced new domestic legislation requiring operators to work with Russia in order to transit ships through the Arctic. So the expansion of NATO is just another element that is adding to that broader context and that broader range of issues that we're seeing up there. So I will stop there, Bethan, but very happy to come back on any questions in a minute.
Thank you very much, James, and thank you very much to all of our speakers. Can I ask the speakers to pop on their cameras and we'll have a bit of a Q&A. Everyone was ready and raring to go there. That was brilliant. So we've had some really interesting discussions and thoughts there, and there's quite a few questions that are coming through in the chat. I think I'd like to start with James Lee. There's this idea of extreme events has come up in a number of the talks, and there's a few questions in the chat talking about extreme events, particularly things like atmospheric rivers. to what extent do extreme events impact things like albedo in Greenland? Like you talked about the albedo changing in Greenland, and is that susceptible to these kinds of atmospheric rivers and extreme events?
Oh, definitely. I mean, for say the example that I used on the North American wildfires, so the heat goes directly onto the ice sheets and so smoke particulate matter. That darkens the ice sheet, which then means that it absorbs more energy, and as it absorbs more energy, it means that it can melt more. And in addition to that, you have the glacier algae. If you have more liquid water on the ice sheets, that means that the algae can grow more, which then further darken. And then also you just have the melting out of the particulate matter that's in the ice. So when snow falls, it generally forms condensating nuclei. So then that can also exacerbate the darkening of the ice. But then also with things like the rain on snow events and the extreme heat waves, that as you get meltwater ponding, as you get more liquid water on the surface of the ice, that generally darkens the ice sheets as well. So because it turns more blue to the closer that this.
James, can I ask you to just lean in a bit towards your microphone?
Yeah, definitely. Yeah. So this blue area where there's all meltwater, that means that the ice sheet is less reflective, so it absorbs more of the solar radiation as well. So yeah, these extreme events, they're not necessarily short-term flash in the pan sorts of things. They really kind of have multi-year, multi-decadal effects.
Thank you. And Ella, you were talking about atmospheric rivers in Antarctica, and there's a question here about how are they measured in the polar regions? How do we actually observe them? How do we know they were there?
Yeah, so atmospheric rivers are kind of a hot topic at the moment, certainly in the Antarctic. So I guess the question as being whether they're a culprit of warming and increasing precipitation. It is something we can measure, and we do that with on the ground measurements, but also we see it with satellite measurements, and increasingly we use lots of modeling, because the measurements to actually detect precipitation in Antarctica are extremely sparse. We have very few observations from the ground, and those that we do have are only in very specific locations. So we rely quite a lot on model products and satellites to define when they're happening. The other thing is that atmospheric rivers are kind of by nature defined by their sort of geographical extent. So they're very these long, thin filaments of moisture. And that means that we need to have a map view of them, basically, to define their very existence. We know that precipitation is increasing with climate change. It's a kind of theoretical consideration. For every degree of warming that we see about 7% more moisture held by the atmosphere, and that means that we get more precipitation. We've seen that in the UK, for example. The last 18 months have been the wettest 18 months on record. And this is exactly what we're seeing in Antarctica as well. We expect that there will be a continuation of more moistening and more rain and snow events in Antarctica. I also saw there was a question about feature tracking, which is another way that we can track atmospheric rivers. It's actually something that I work on right now, and we can use integrated vapor transport, or basically how much moisture is moving through the atmosphere, using a bunch of new kind of tracking algorithms that are really helpful for applying to either model data or gridded observation derived data.
Yeah, interesting. I'm going to take this point about feature tracking and run with it to Hamish. I asked you earlier about how we know that we're losing glacier area and volume. Are we seeing glaciers flowing faster in the mountains, or is this something we're mainly seeing happening in the Antarctic ice sheets around the edge of the Antarctic ice sheet?
Yeah, it's mostly in the mountains, mostly a slowdown, and that's because the flow of ice in glaciers that aren't floating or near floating is driven just by gravity. It's gravitational flow, and so the important things there are the ice thickness and the steepness of the surface slope. And so as the glaciers thin, their flow slows down, and so especially in the Himalayas, more and more areas of stagnant ice that's just pretty much flat and covered in rock debris sitting there melting down slowly and vertically. but not flowing anymore. So it's sort of the opposite effect as a slowdown rather than a speed up.
Okay, and then what have we seen in Antarctica?
Oh yeah, so actually, for me as well, yeah, certainly widespread speed up. All of the Antarctic Peninsula glaciers, which are tidewater as well as the big outlets, acceleration in their flow, and acceleration particularly in the West Antarctica, the major outlets of West Antarctica. And it's also driven by primarily thinning, but in that case, because they end in the sea and they are buoyant, as they thin, they start to float off the ground below, and so the friction is reduced at the base, and that allows them to flow faster. So that it's the same driver, thinning, but because they end in the sea, it's a different result, acceleration.
Okay, thank you. And Mike, we're going to stick with this idea about thinning. And there's been a question about how do we know that the ice shelves around Antarctica are thinning? How can we measure that?
Yeah, so it's a good question, and the answer once again is satellites mainly. We have satellites orbiting the Earth that go around every 90 minutes, and there's a couple of different types that can tell us about ice shelves. If you can imagine, we know kind of the iconic thing about an iceberg. If you can measure how much is above the surface, you know how much is below the surface because you know the density of ice. Well, an ice shelf's the same. If you can work out how much is above sea level, you can work out how thick it is. And so actually these satellites orbit the Earth, and they send down either a laser beam or a radio wave, measure the time that comes back, and they can then measure where the surface of that ice shelf is. And they're doing that millions of times a year over the whole ice shelf and all the ice shelves. And so we can put together maps of how those ice shelves are actually going down because they're getting thinner, and so less of them is above what we call the freeboard. You could say, should we rely only on satellites? Well, there have been a few missions where people have sent submarines underneath them. These are robotic submarines carried on research vessels, and they've been showing exactly the same thing. If you go underneath them, we can show that they're thinning at the rate that the satellites tell us.
And this is Boating McBoatface.
Yeah, so everybody wanted the Sir David Attenborough to be Boating McBoatface, but the submersible, the autonomous submarine, is actually what got called Boaty. So,
Mike, I'll stay with you if that's okay. In your talk, you talked about, you had a picture of Antarctica and a kind of cross section of Antarctica with an ice shelf and the ice sheet. And you also talked about high magnitude, low impact events. I was wondering if you could expand a little bit on what some of the key feedbacks that we might see. You talked a little bit about retreat into grounding lines, driving further retreat on a reverse bed slope. I guess the question is, have we seen this in the past? And are we able to, how accurately are we able to say what the threshold is? So right to the heart of the problem here.
Yeah, okay, so there's a couple of bits of ice sheet physics. One is that we're confident for the reasons that Hamish said, that as you start to thin the edges of glaciers that terminate in the sea, they accelerate. And that leads them to thin some more, particularly if they're on a slope that's sloping back, getting deeper and deeper into the interior of the continent. So they'll retreat, and we get a runaway feedback, and that's called the marine ice sheet instability. And there are some people who are worried that this is happening already. This has started. That's being debated, whether that's actually started. I think most glaciologists think we're close, but not there yet. It's likely that's happened in the past. There is evidence for much higher sea levels around the globe about 125,000 years ago, when the climate was pretty much where we're heading towards in terms of temperature. It was a little bit above Paris. So we think that in the past there has been a marine ice sheet instability, and it's definitely happened. That low likelihood high impact storyline, I showed that dashed line on the sea level curves, that comes from a more controversial bit of physics, which is saying that whether or not an ice sheet's on a reverse slope or on a flat slope or even on a forward slope, there might be a situation where if the ice shelf's lost, it starts to basically break up in an uncontrolled fashion. That's called the marine ice cliff instability. We don't know if that applies or not. We don't know if it's applied in the past, and we're looking for instances in the present. It's controversial, but there's enough concern about it that it's appeared in the IPCC reports as a scenario we can't yet rule out.
And James Lee, I'm going to circle back to you. This marine ice cliff instability, is this also a concern in Greenland?
So it has been suggested that there is some evidence for the marine ice cliffs instability. It's also referred to as Mickey. So I might just use that just to stop them getting high. So there has been some suggestion that there is evidence for it in some glaciers in Greenland. We're talking like 2 or 3, but it's 2 or 3 of the big ones that account for about 30% of all iceberg discharge from the ice sheet. But what we're also seeing is other processes that happen next to the glacier that then mitigate those impacts. So when the ice breaks off from the glacier, that ice also has to go somewhere, and generally it just sits in the fjord in front, and that can actually cause a backstress on the ice fronts as well. So that can actually help prevent further destabilization of the ice fronts, which then means that the Mickey, the ice cliff incident, might not be as big an impact as we think. But as Mike said, it's still very much an open question. It'll probably vary from each glacier to each glacier. So yeah, each glacier is its own different thing. So it might be that it happens in some areas but not, or it might not be an issue at all, or it might end up happening everywhere. We still don't know yet. We still just don't have the observations.
Sounds like more research is needed on this. Sian, can I ask you a question? It's in the chat here, and the question is, I think the question is getting at, to what extent is the warming that we've seen forced by astronomical forcing, and to what extent is the astronomical forcing in the future likely to offset the warming, the radiative forcing coming from the greenhouse gas emissions?
The astronomical forcing in terms of, say, orbital forcing.
Yeah, I think the question is getting to Milankovitch forcing.
Yeah. All the typical parameters that we think about for Milankovitch cycle, so eccentricity, tilt, and precession of how the Earth moves around the sun, the periodicity of those changes, the shortest period for that is 22,000 years or so. So the current rate of warming that we're seeing over the past 150, 200 years can't be explained, but by the long term, so long, it's beyond Holocene time period even. So the current rate of warming is definitely not controlled by astronomical changes that we're seeing. In terms of how much it can be offset by that change, I'm a bit scared to think about that, because I need to be thinking about human lifetime horizon in the next few decades, next 100, next 200,000 years, whereas to put hope on the astronomical orbital changes, that's looking at too long of a time horizon for myself, for my children, for my potential grandchildren, and for all of us. So I wouldn't count on that.
Don't rely on orbital forcing. Right. Okay. I'll stay with you, because you were talking about floods in the Himalaya, and there's a question about, let me just find it. Is the flood risk that we're seeing from glacier lake outburst floods in places like the Andes and in the Himalaya, and maybe Hamish, you might want to come in on this as well, is that flood risk likely to grow, or is as the glaciers shrink, is the risk likely to decline? Like, how is the risk of flood likely to evolve as the glaciers on different timescales as the glaciers change? I'll start with Sian and then I'll go to Hamish.
Yeah, I think on the relatively shorter term, the risk is likely to grow, because with melting of glaciers and also more precipitation falling in liquid rather than solid phase, which will prevent glaciers grow even in winter season, we're going to see formation of new glacial lakes, but also deepening and widening of existing glacial lakes, which will lead to increase in glacial lake outburst flood. Whereas if we look at a much longer term with, especially if we think about what's happening in the tropical region, tropical glaciers now, a lot of these glaciers have shrunk so much, and some of them have melted away so much, we're unlikely to see further increased risk of formation of new lakes and deepening of existing lakes. But I think in the shorter term, we're still going to see an increase in glacial lake outburst flood risk.
Okay, thank you. Let's go to Hamish and ask him about the longer term.
Yeah, well, I think there's, I suppose, the key thing about these, especially the glacial lake outburst floods, is that they result from collapse of the moraine dam. So if the terminal moraine gets left behind as the glacier retreats, and the water ponds behind that, and then eventually, because it's the moraine dam is just made of mud and rock, it's not very mechanically strong, so it can potentially fail. Of course, when it does fail, it's a one-off hit. So the lake drains, and then the dam is gone and it can't refill. So there's a sort of there is an end point to all of this, which is when they've all failed. Having said that, there are an awful lot out there, particularly in the Himalayas, and 90,000 glaciers in the Himalayas, not all of which have the potential to have this kind of configuration where they've got a moraine dam that's ready to fail. But you know, a lot of events yet to go, and they're you know, they're catastrophic in nature, so it's difficult to predict. They tend to be in response to a particularly heavy loading, perhaps from an extreme rainfall or a strong melt event, or maybe a landslide or earthquake. So they kind of linked to those other things, but inherently pretty unpredictable. So I think the hazard, it'll increase over at least the coming decades. Ultimately, it'll decrease as the ice and the you know, as the ice disappears, and then the moraine dams, the ones that are going to fail, do fail.
It's kind of this idea of a paraglacial response to the landscape, isn't it? As the glaciers disappear, eventually the response of the landscape to that will trail off. And what we're seeing with these gloughs is perhaps a landscape response to the removal of the glaciers. And there's an interesting question that's about, when you've had a glough, it can wipe out a lot of natural history, biodiversity, natural heritage. And we've talked a lot about people and how they might be affected by these outburst floods. But is there any idea about how we can do geoconservation to protect the natural heritage of these areas, the natural resources in the areas? If anybody wants particularly to answer that question, feel free to indicate that to me. Otherwise, I'll go to Hamish.
Yeah, that's a difficult one. I think they're relatively, in terms of the range that they operate over, that they're damaging over, it's limited to some extent, because you get a very high wave of floodwater where the rivers are constrained within within the mountains, within the foothills, and then when it can spread out onto the floodplain, then it's dissipated. So the real impact is in that, you know, the first few tens of kilometers perhaps of downstream of the glacier, and they are particularly damaging for hydropower and irrigation schemes and villages who any habitation that's near the water level, extremely at risk, and also road crossings. So I know a bit about that. I don't. I mean, they scour the channel completely and leave a lot of debris. So everything that's there is removed effectively in direct line of the flood. And then I suppose it's an opportunity for the landscape to reset.
I guess what we should really be doing is trying to minimize how much the glaciers melt in order to reduce the number of outburst floods to the minimum that we can.
In one of my slides, I showed this enormous expansion in use of the rivers for damming, for hydropower. And I suppose another potential knock-on effect of the outburst floods is that they could destroy those bigger those dams downstream and have a cascade of floods. And I think that it's certainly something which the developers of those hydropower and irrigation schemes really need to take into account is the risk that they're putting their infrastructure to, and also the potential risk for larger populations downstream if they fail.
Okay, thank you. Yeah. I'm going to come back to Mike. There was a question, Mike, about how can we measure glacier change or ice sheet change over centuries. Hamish has told us about feature tracking and glacier remote sensing over the satellite era, but we've only had satellites since the 1970s. We've only had good satellites, regular satellites going over every few days, fairly recently. So how do we know what happened before the satellite era? And how can we reconstruct glacier extent and area over that longer term timescale?
Yeah, thanks, Bethan. So yeah, we can reconstruct prior to the satellite era. We can go a little bit further back with human observations, the early explorers and so on. But then you're into the realms of what we call glacial geology, which is looking for the evidence of where the ice sheet was in the past. So the ice sheet, when it's a bit thicker, leaves the equivalent of a geological tide mark. It might leave scratches on the rock or debris that's been left behind on the rock. And we have techniques for working out how long ago that debris was left behind, sometimes using radiocarbon dating that you may have come across with many other things in life, such as archaeology, but actually we use cosmogenic surface exposure dating quite a lot, which is a technique for taking a rock and working out when it was left behind out of a bit of ice. So we can piece together how the ice sheet has changed from effectively centuries right the way back to millions of years ago. And we're piecing together quite a complex story about how the ice sheet has changed in the past, including, as I said, some instances where it may have been as small as what we're worried it's heading towards now during some warmer interglacials.
James Johnson, I'm going to ask you a question about the Arctic and the future of shipping around the Arctic. You mentioned it briefly in your talk about the geopolitical ramifications of the Northern Passage opening up. I wondered if you could expand on that a little bit.
Yeah, thanks, Bethan. Yes, I mean, the melting sea ice raises the prospect really of the opening up, in particular, of the Northern Sea Route. I mean, there are several sea routes actually that run through the Arctic. I mean, if I just share my screen, I can show you a slide actually on that. If you can see that. So yeah, so there are a couple of potential sea routes through the Arctic. So on the left-hand side, you've got the Northwest Passage, a little bit more difficult to navigate, generally more ice filled. On the right-hand side, you've got the Northern Sea Route, which generally people talk about when they talk about retreating sea ice and a potential for navigable routes through the Arctic. I think the suggestion is that we could have ice-free summers at some point in the 2030s, which might allow the passage of ships along the Northern Sea Route. And you can see that that's quite an attractive thing. If you look here at the line in green, you can see the kind of, regular global shipping routes. You'd cut a couple of thousand kilometers potentially off your shipping route and save about 30% in time, and of course in fuel as well if you're shipping between Europe and Asia. I think the reality is, stop sharing now, that those routes will continue to be very high risk. A number of operators have said that they are not at this point thinking about using them for environmental reasons, but also for geopolitical reasons. And one of the consequences, of course, of using the Northern Sea Route is that it takes you right past Russia, and so we can expect, I would imagine, quite a lot of sort of Russian vessels and traffic through there, and states that are comfortable working with Russia. But I would imagine that there are others who would be a little bit more cautious about doing so. And as I mentioned, Russia has introduced recently new regulations which kind of set out their expectations about what ships should do when they're traversing the Northern Sea Route. We are seeing more vessels in the Arctic generally. So over the past decade, the number of vessels has gone up from about 1,300 to about 1,700. But as I say, it hasn't taken off yet. And I think, those are some of the reasons that probably explain why. At some point, of course, the ice will retreat sufficiently for vessels to be able to traverse the Arctic straight over the top. And that will take you primarily outside of national jurisdictions. So that is, however, much further into the future.
And in the last couple of minutes, I'm going to ask each panelist just to give us a very quick take-home message. So just one sentence each, if you could, on a take-home message. So James, can we start with you? James Johnson, we start with you. A quick take-home message from the session that you've had today.
I think the importance of maintaining in our minds that long-term vision of the polar regions as places of peaceful cooperation and science. I think that that is so important in terms of underpinning our collective understanding of the polar regions and what happens there will affect us all. So if anything, that's a really strong argument for working collaboratively and cooperatively.
Thank you, James Lee.
So it's an oft-used line that what happens in the Arctic doesn't stay in the Arctic, and same with the Antarctic. And all the mountainous regions where there's glaciers. And some of the stuff, or quite a lot of the stuff might sound quite doom and gloom, but it's still within our capability to decide as a society what path to go down. And the worst case scenarios that we're looking at, or even some of the bad case scenarios, it's within our power to actually do something. So that would be my take-home message.
Thank you. Positive. Sihan.
I think what James just said kind of echoes with what I said in my last slide. So I'll say something different. I think from thinking about this hazard in the mountain cryosphere changes, it's super important to recognize the importance of working across disciplinary boundaries, because what happens in the climate system will directly influence the Earth surface process as well. So we are seeing this melting of mountain glaciers and changing patterns of weather and climate influencing land surface process and leading to things like landslide, mudslide, flooding events, glacial lake outburst flood. So it's super important to work collaboratively across disciplinary boundary and also beyond academic realm as well, working with government, NGOs, and different organizations of those affected regions to make effective changes in terms of mitigation, adaptation, forecasts, and projections.
Thank you. I believe it's interdisciplinarity. Hamish, just a very quick message.
Yeah, I'd echo a message that came from several people. One, I suppose, a point to make would be that a lot of the systems we've considered, like Arctic sea ice or sea ice in general, and the ice sheets, have inbuilt these non-linearities, these tipping points where change drives them beyond a threshold. Mountain glaciers are different. They're largely linear response to temperature. And so those in particular are really within our control. Any increase in temperature leads to a linear decrease in ice, and it's potentially reversible. So if we could get control of that temperature rise, then we really can stop the change and even potentially in a long distant future reverse it.
Thank you. I think that point about reversibility is important. Mike.
Yeah, I think we're coming up with a similar message, which is we have choices. Every ton of CO2 that we don't emit is some ice that's not melted. And so we should always keep that in mind, that we are committed to some sea level rise from ice sheet and glacier loss, but we have choices to how much. We need to be careful of getting too close to the tipping points, such as the loss of the West Antarctic Ice Sheet. But we have a choice about this.
We have a choice. Thank you. Ella.
Hardest to finish after everyone said such great stuff. But yeah, I think my take home would be that climate change and extreme events are already reshaping Antarctica and the polar regions in general. These are having pretty disastrous consequences already at the level of warming we've already seen. They will continue to get worse for as long as we continue to emit greenhouse gases and we continue to transform our climate. But we do have choice in where we end up. We can make it less bad. And I think, yeah, that's the most salient point.
A very consistent message. It's a choose your future message from everybody. Every ton matters, every 1/10 of a degree matters. We have a choice, we can control our future. I'm not getting a sense of doomerism or negativity. There's a lot of positivity here. I want to thank all of our panelists, all of our speakers, really very much for coming and speaking. So thank you so much for giving your time, giving us this really interesting talks. I've really learned a lot. You have all had really excellent insights. And thank you to the Royal Meteorological Society for hosting and running and organising the event. So thank you very much, everybody. I don't think we actually have a clapping emoji, so you'll have to just clap yourselves. But I think that's about all we have time for. We're scheduled to complete at 14:30. So yeah, thank you very much, everybody.
Thank you.
Yeah, thank you. Bye,
Thank you, Bethan.